Okay, welcome everyone to the first of possibly many video tutorials for this class. The point of these tutorials is to go over some of the coding essentials that you're going to need for all the assignments, but also just everywhere along your machine learning journey. Um, so today we're starting with NumPy. NumPy is probably the most important thing you can learn if you plan to go into machine learning, or even just any sort of scientific computing task. So if you're going into physics or you're going into data science or anything like that, you'll want to know the basics of NumPy. So why are we using NumPy? The main reason is that basically all machine learning models end up using a bunch of matrix vector products. So neural networks, even though they look really complicated, basically just boil down to multiplying matrices and vectors together and then adding vectors. And it turns out that NumPy provides us a really nice library to do all this stuff. So instead of coding all this stuff up from scratch, you can just use NumPy and it'll do it for you. The second reason is that NumPy is written in C. So for those that don't know, C is a much faster programming language than Python. It's a lot more flexible in what it allows you to do, which means you can write code that's a lot more efficient. So basically, instead of actually using Python code, you're using Python code to call C code, and the C code does the work and spits back the answer for you. So that makes your code a lot faster, which is really important because machine learning code can be quite slow. So we want to save any second we possibly can. And it's also more efficient in terms of memory, so it'll have a kind of smaller load on our laptop or eventually GPU if you're running a big model. Finally, NumPy is everywhere. It's kind of unavoidable. This is a skill you're going to have to know, so you might as well learn it properly during this course. I'd really recommend avoiding using, ChatGPT and Gemini to run your code. I get that it's very efficient and it's probably going to be part of your toolkit when you work, but often it's actually faster, in my experience, to just solve the problem yourself and then be able to solve it every subsequent time it comes up instead of just calling on an AI model to help you out every time you do something. With that, let's get straight into the kind of crux of this library. So everything in this library revolves around this data structure called an ND array. So it's basically just a NumPy array. You might have heard the name array before from other programming languages, like Java uses this thing called an array. But basically, it's just a grid or list of numbers. More like a grid, I'd say, because it's kind of a fixed size. It's not like a Python list, which you can have nested lists of different sizes and stuff. It's a bit more rigid. But basically, NumPy lets you have arrays with any number of dimensions. So here we go all the way up to a 3D array. You could have a 4D array, 5D array, 6D, whatever. Those are just a bit harder to visualize. So here we're sticking with 3 as our maximum dimension. But you'll definitely see higher dimensions in code. So really the key thing I wanted to point out with this image is this idea of shape. So shape is going to come up a lot in your code, and it's really practical to understand the shape of an object. You don't have to understand all the numbers contained inside, but just knowing the shape will kind of help you understand how the array behaves. So here we have the shape listed under each array. This first one is just a 3-dimensional array. The syntax might look a little bit weird. Why is there a trailing comma? I'll explain that a little bit later. But basically, it just has to do with the way that NumPy, the values that NumPy returns. So here we have a 2D array. Why is it a 2 by 3 shape? Because it has 2 rows and 3 columns. So that's how we talk about matrices too. We say the number of rows first and then the number of columns. Finally, 3D arrays can be thought of as basically a stack of matrices. So we have a stack here of 2 matrices along this 0 axis. So that's where this 2 comes from, 2. And then each matrix has shape 3 by 4. So that's it. Okay, so 2 by 3 by 4. So those are the basics. We're going to hop into some code in a moment, and we're going to see how we can actually obtain these objects in code. And then we're going to see the different kinds of things we can do with them. And hopefully you'll start to understand why this library is so popular and so powerful. So I provided a Google Colab link here in the slides, but I also have the link in the description of this video. So I just have it open already in another tab. You might not be able to edit the document. You might have to make a copy and then you can edit that yourself. But with that, let's get started. Okay, So we're in the NumPy tutorial document right now. And before we get started, I'm just going to introduce Google Colab because this might be a new tool for a lot of you. So Google Colab is essentially Google Docs, but for Python code. Specifically, it's for these types of files called Python notebooks. So this is what they look like. And the reason they're called Python notebooks is because unlike regular Python files, which are just filled with code, this is kind of just a normal notebook where you can write text, but you can also write code, specifically in Python. So actually, the file extension here, which we expect you to submit all your assignments in, is .ipynb. So I means interactive, Py means Python, and NB means notebook. So this is an interactive Python notebook. So you can do all the regular things you do in any kind of Google document, plus some extra features like running code. You can share this with people. It's really, really practical. You're going to be using this all the time. So I'm going to go through some tips throughout the video on kind of useful features that you should know about when you're working with this. For example, you can have a index here. So if you're using this document right now, you can jump around the index and find sections that you want if you ever go back and refer to this document. With that, let's get started. Oh, and also this thing here is Gemini, the coding assistant. Please try to avoid using it. I don't think there's a way to just remove the button. I wish there was. Maybe there is, but anyway, please don't use it. Anyway, okay, so let's get started. So I already introduced this idea of the array, and I told you that there's kind of this weird syntax with the array where it returns, for some reason, for the shape of a 1D array, 3 with a trailing comma. So what does that come from? Basically, the shape is this data structure in Python called a tuple. So you might have heard of this before. A tuple is just a list of numbers. So it's something like this, 2, 3, 4, 5, right? This is different. So this is not equal to a list, which is a list of numbers like this with the square brackets. So tuples are of a fixed size, lists are not. Okay? So basically, the thing is, if you want to indicate that you have a tuple with just one element in it, you actually have to put a comma after the 3. Okay? We can see that by just writing type and printing this out. We see it's a tuple. If I remove this trailing comma, it's going to think I just have a number with brackets wrapped around it. So it's just going to think this is an integer. Okay? So that's the idea. So the trailing comma kind of looks a little bit weird, but I promise you it's nothing to be afraid of. Okay. So with that, let's initialize some of these arrays in NumPy code. So the 1D array is by far the most straightforward to initialize. You're going to have to import NumPy first. Please, if you're following along, make sure to at least run this cell because you need to import the NumPy code to be able to run all the other cells in this document. So how do you run a cell? If it's your first time ever using a notebook, there are 2 ways to do this. The first way is by clicking on this Run Cell button, but I actually recommend using Shift Enter. It's just a lot faster because you can run a bunch of cells in a row. You can go through, just keep on holding Shift and spamming Enter, and you'll run a bunch of them. So it's a nice, convenient way to do things. In general, when you code, it's better to just use your keyboard for everything if you can. Yeah, so that's just a little thing. So what are we doing finally inside of this cell? So we're importing NumPy, and then we're initializing a list of numbers. So this is just a Python list. There's no NumPy yet, okay? Here is when the NumPy comes into play. What we do is we take this np.array function, which just takes a list of numbers and turns it into a NumPy array. So it converts from Python list to NumPy array. Okay, so we just feed it in, and then we can print it to the screen. So this is something that might be unfamiliar if you're not used to notebooks. You can actually print things to screen by just writing the name of the variable, which is a lot faster than doing something like print. It's also often going to print things in a nicer format than print would. So a lot of objects kind of have a special way of displaying if they know that they're inside a notebook. So I recommend almost always writing it like this, unless you absolutely have to print. Down here I have to print because I want to print multiple things. You can only display one thing by writing the name of the variable. Here I want to print multiple lines, so I'm using print. Anyway, so I'm just going to run this cell. And then what we're going to do is we're going to inspect a few interesting attributes of this type of object. So we now have A is an NP array. So if I just, an ND array. So if we do type of A, we see it's a NumPy ND array. So it turns out it has a bunch of attributes that are interesting for us to look at whenever we're working with NumPy arrays. So the first key one is the shape. So I introduced the shape earlier. If I take A and I print its shape, then I get 3, which is exactly what we saw in the image above. The next thing we can do is print the number of dimensions. So we write that as ndim, and if we run that, we see 1. That makes sense, right? We have a one-dimensional array. There's only a single dimension. The numbers run along. Okay. Next is the size. So size is just the number of elements inside of the array. So if I do a.size and I print that, I see 3. Why 3? 1, 2, 3. Pretty simple. And finally, dtype. So dtype is the type of data stored inside of the array. So in this case, we only have integers. So if I run a.dtype, we see int64, which means it's a 64-bit integer. If you're not really familiar with data types in computers, that's okay. It's not really essential for this course. But later down the line, you might want to be able to keep in mind your data type, because your code can be a lot more efficient if it stores data in a more compressed format. So here we have 64-bit integers, but ideally, for example, 32-bit integers would be more efficient. But anyway, not too important, but just something to keep in mind. Okay, so we've gone over all of this stuff. I'm not going to read out loud to you. You can read yourself, but I already said it out loud, so no need to pause the video and read what's said here. What I've done here is I've just taken that code and I've wrapped it in a function so that whenever we have an array, we can print all this information to screen automatically instead of writing it all out by hand every single time. Okay, with that, we're going to print out, we're going to initialize a 2D array. So how do we do this? If you're familiar with Python, then, or really any programming language, you know you can represent a matrix as a nested list. So just a list containing 2 lists inside of it. So for example, if I wanted to make a 2D array, I would make my first list, and then I would print my second list. So this would be the matrix 1, 2, 3, 4. Right? So that's what I'm doing down here, except it's a bigger matrix. I don't want to type out the whole thing in front of you, but we can initialize it just like that. So here's the first row, and here's the second row, and we can print it to screen. Okay, so nothing too crazy. Before I even run our function that we defined earlier, I'm just going to ask you, maybe to pause the video and think about it, what are the shape, number of dimensions, size, and data type going to be? Well, shape is right there. There's the answer. Number of dimensions is 2, right? 2 and 3, those are the 2 dimensions. The size is 6. Why 6? Because there are 1, 2, 3, 4, 5, 6 elements inside of the array. And finally, dtype. So dtype might trip you up if you haven't done any computer science before, but it's going to be floating point. So what is floating point? Floating point is what we call real numbers in a computer. So here, unlike our first array, which is just whole numbers, here we now have decimals. So when you have decimal places, we call it a floating point number. This is something you should know, just because the name comes up a lot, and there are a lot of interesting problems that come up in computer science when you're dealing with floating point numbers. So anyway, so if we print it out, it should be exactly what I said, 2, 3, 2, 6, and floating point data type. Okay, finally, our 3D array. So how do we code this up? Well, like I said earlier, a 3D array is a stack of matrices. So basically, we're just going to make a list where the first element in the list is this first matrix on the top. And then the second element of the list is this second matrix down at the bottom. And that's it. And again, we can print it to screen. NumPy does a beautiful job printing it. It's a lot more legible than my initialization code up there. And yeah, you can imagine how you might extend this to 4D, 5D array, but it gets a little bit cumbersome. We'll see later there are nicer ways to initialize things, but I think this is the most intuitive way for a beginner. And finally, if we print our info, hopefully none of these numbers are too surprising. So our shape is, of course, 2 by 3 by 4. Our number of dimensions is 1, 2, 3. And then our size, again, is the number of elements inside of the array. So that's going to be 2 times 3 times 4. Why? We have a stack of 2 matrices, and each matrix contains 3 times 4 elements. Okay? So nothing too crazy there. So those are really the basics of initializing arrays and inspecting all the attributes inside of it. Okay? With that, we're now at our first exercise. Oops, I've shown the answer here. Pretend you didn't see that. It's a bit of a trick question, but I'm asking you to predict what the shape, number of dimensions, size, and type are going to be for this array. Now, as a little hint, take a look at the number of brackets here. So what will the shape be? What will the number of dimensions be? What will the size and type be? Okay, so I'll give you a moment to pause the video and think about it. Okay, hopefully you've thought about it by now. Let's see the output. So our shape is 1 by 1 by 2. Why do we have 3 dimensions here? It's because we have 3 square brackets. So think of each pair of square brackets as adding a dimension to your array. So that's why we have 3 dimensions. The size is 2 because we have 2 elements inside of it. And our type is float 64 because we have floating point numbers. Whenever you see a decimal, it means the type is float. Okay, float is short for floating point. Okay, so that's it with the first section, which is all about initializing arrays in kind of an intuitive way. Now we're going to look at this idea of reshaping arrays. So what is this all about? So basically the big idea is if we have just a list of numbers like this, we might want to reshape it into a matrix. So we might take this data and go to this 2 by 3 array, where the first row is 1, 2, 3, the second one is 4, 5, 6. So we've kind of taken this first part and pasted it there, taken the second part and pasted it there. So how do we do that? It's really simple. So if we have a variable called data, then we just do data dot reshape and then the new shape that we want. And we could do the opposite. We could do 3 by 2 instead of 2 by 3, and we get this matrix. So this is a lot more practical. You might want to start with just a vector and then reshape it into a matrix or a tensor afterwards. This is very common in code. You can also do the opposite. You can take an array, or a matrix, I should say, and turn it into a vector. Okay, so here's the code of how you'd implement this stuff in the image. You would initialize an array using exactly what we did earlier. We can print it to screen if we want, and then use the reshape method here. You can also use a function. So here we're using a method on the object called data.reshape. We can also use this function np.reshape, where we feed as input a means array, called data, and our new shape, which is going to be 3 by 2. So whichever one you find nicer to work with. Typically, you're probably going to see the method version. Okay. Our next exercise, by the way, I didn't run any of these cells. The output's displayed because I ran them earlier. We're going to get an error on this because I haven't run the cell yet where data was defined. So the order in which you run the cells matters. So I can't run this cell because data is defined up here, but I haven't run this cell yet. So I have to run this, then I can run this, and I can also run this. Okay, so here's another exercise. Again, I'll give you a moment to pause the video and think about it. But the question is, will the following code work? Will we get an error, or will this work just fine? So we have our same data object from up here, which has the numbers from 1 to 6. And we want to reshape it to size 3 by 3. So is that going to work? Okay, hopefully you had some time to think about it. The answer is no. So let's try to run this. Let's see what happens. Actually, I'm just going to show the output from when I ran it earlier. No. Why? Because we only have 6 elements in the array, and we're going to try to turn it into a 3 by 3 matrix. A 3 by 3 matrix has 9 elements in it, but we only have 6 in our vector, right? So basically it's too small to be reshaped to that size. Similarly, we'd have an issue if we tried to reshape it to something smaller, like a 2 by 2 matrix, right? Because we have 6 elements, but a 2 by 2 matrix has 4, okay? So hopefully that reshaping stuff wasn't too complicated either. Okay, now we're going to get into some more convenient ways of initializing arrays. So we saw this method earlier of just taking a Python list and feeding it in, and transforming it into a NumPy array. But it turns out a lot of the time this can be a real pain in the butt. For example, what if instead of just having the numbers 1, 2, 3, 4, 5, 6, we wanted the numbers from 1 to 100, right? There's no way I'm going to write out the full list of numbers from 1 to 100. Okay, so how do we do that? Let's take a look. So this is the way we were doing things earlier, as said above. The first way to do things is using this built-in function called np.arange, okay? And if you're familiar with Python, it's very similar to Python's built-in range function. So how does range work? Just to refresh your memory, you give it a starting number, you give it a stopping number, which is not included. So that means we're going to include the numbers from 0 to 9, not 0 to 10. And you give it a step size. So this is basically how big of a jump you make between each step. So step size of 2 means we're going to print the numbers 0, 2, 4, 6, 8, which is what you see in the output of this cell. Okay, so the np-arrange function works in a very similar way. The name arrange comes from the fact that it returns an array. It returns an array representing a range. So we call it a range, right? So the A comes from array, range comes from range. So all you do is you use the exact same format as before. Start 0, stop 10, step 2. And if we print it, we get an array containing all the numbers we printed earlier, okay? So if I wanted, for example, the numbers from 1 to 100, I could do np.arange. I said 1 to 100, so I'm going to write 101, right? And my step size is going to be 1. You don't actually have to include that. That's the default step size. By the way, you'll notice here I didn't write start and I didn't write stop. These are optional. You don't have to write start equals, but it's a nice way to make your code a lot more readable. So if you go back to it, you know, okay, the first argument represents the start, the second one represents stop, and the last one is step. This is a little bit less readable. With a range, it's not so bad, but with more complicated functions, with more complicated APIs, you might want to use these keywords. So here I get the list of numbers from 1 to 100. Okay. The next option is np.linspace. So linspace works very similarly to a range, except instead of only giving you integers, so with a step size, for example, like we said, of 1, 2, 3, 4, you can get real numbers. So the simple example down here is we go from start of 0, stop 1. This time, stop is inclusive. I don't know why. And num is the number of numbers within that range. So basically, we're going to take the range of numbers from 0 to 1, and we're going to chop it into 3 pieces. So we get the numbers 0, 0.5, and 1, right? So as another example, let's say we wanted to go from, I don't know, 0 to 0.9, and we wanted it in 4 pieces. Then we get 0, 0.3, 0.6, 0.9. Okay, so this can be convenient as well. One final example, 0 to 10, and we want it in 11 pieces. Or sorry, 0 to 1, let's say. Then we get 0, 0.1, 0.2, 0.3, all the way up to 1. Okay. Where does the name come from? I find it really convenient to understand the name so that you don't have to really memorize as much. Linspace stands for linear space. So we have a linear space of numbers that we chopped into an even number of pieces, or evenly sized pieces, I should say. Okay, finally, one more thing. A lot of the time, you're going to want just a matrix filled with 1s or with 0s. So for example, with 0s, you might leave 0 as a placeholder and then fill in the matrix later with new numbers. How do you do this? Pretty intuitively, you write for 1s, np.1s, and you can specify the shape. So here we just have a 5-dimensional array. But we could also specify that we want a matrix, so 5 by 5 matrix here of 1s. Same thing with 0s, exact same logic. Again, you can specify any number of dimensions. So we can do 3 by 3 by 3. We get this bigger thing here. Okay. So nothing too crazy so far. Okay, so a little exercise. Create the following array using arrange and reshape. So I'll give you a moment to pause the video, try it out, use this cell to write your code. Okay, so let's take a look at the solution. It's not too bad. We just specify that the range starts at the number 3, ends at 7. Why 7? Because it's actually going to end at 7 minus 1, which is 6. And we want to reshape it to be a 2 by 2 matrix. So that's it. Okay, next up, we're going to be working with arrays. So let's take a look at that. So we've seen kind of how to work with the shapes of arrays. We've seen how to initialize them. Now let's see how we can use them for something practical. So the first big thing that's really nice about NumPy is it lets you add arrays or subtract them or multiply them or divide them element-wise, which means we basically, add 1 plus 1 equals 2, 2 plus 1 equals 3. So elements at the same indices get combined together using some sort of operation. So if we wanted to code up this stuff in the diagram, we simply initialize our data array using whatever method we want. We could have used arrange here if we wanted to, but that seems like overkill. We can do np.ones to initialize these ones. Then we just add them together to get this array with 2 and 3. So we literally just do array 1 plus array 2 to get array 3. Okay. Now, this might not seem like a big deal, but let's think about what the alternative would have been if we didn't know we could do this. Instead, we'd probably have to define some function that takes 2 arrays as input and then loops through adding together both of the elements and filling up some other array. So this syntax is way faster. So we can do something like data divided by ones. We should get back the same thing because we're dividing by 1. Oops, I didn't run this cell. That's why running cells is important. We do ones divided by data instead, just to make it more interesting. We get 1 divided by 1 is 1, and 1 divided by 2 is 0.5. Okay, so hopefully that's not too crazy. So again, you can add, subtract, multiply, divide. You can do other things too, maybe this is a bit too quick, but we can also even use the greater than operator. So it's going to check for each element of data, is this element greater than that one? And it's going to return a Boolean telling us whether it's true or not. So is 1 greater than 1? No. Is 2 greater than 1? Yes. Okay, so probably any operator you can think of can be used between 2 arrays. Let's see, I've never even tried this. Let's try the modulo operator. So for those that don't know, modulo gives you the remainder when you do division. Here it's probably not really going to do anything because we're dividing by 1, but it works. Yeah. Okay, cool. Next, so let's just look at some more examples. So I actually kind of just showed you how to do this above, but we can subtract, multiply, divide. We can do everything with arrays, okay? It's a lot cleaner, right? We don't have any loops anywhere in our code. It turns out that under the hood, it's a lot more efficient to let NumPy do the work for you than for you to try to implement it yourself, right? Because again, earlier I said it's written in C code, and C is a lot faster. And here we're just showing off that we can do this with higher dimensional arrays, right? So let me just actually print what one of these looks like. So X is a matrix, and I don't know if this will work. Yes. X and Y are both matrices, and we can add them together in exactly the same way. So what do we expect? We expect the output to have the number 1 plus 5, which is 6, 2 plus 6, which is 8, 3 plus 7, which is 10, and 4 plus 8, which is 12. Beautiful. Okay, I showed you a little bit of this earlier as well. You can also use logical operators. Again, nothing special. Like I said, these are just random ones I decided to show you. Probably any operator you can think of can be used between 2 arrays. Okay, now note that for AND, we use the ampersand sign instead of in Python, we literally type out the word AND, right? AND is a special keyword. For NumPy, you're going to use the ampersand, and for OR, you're going to use the pipe operator. This is common in other programming languages, so if you've used those, it shouldn't be too big of a deal. But let's look at some examples here. So let's initialize A. Oops. Hold on. That's actually A equals NP dot, I want the numbers from 1 to 6. So what do? I do 1, 7. I print it out. Okay. So for example, we can check where A is greater than 3. Okay. And what that returns to us is a new array where each element of the array indicates whether that number was greater than 3. So is 1 greater than 3? No. Is 2 greater than 3? No. Is 3 greater than 3? No. Is 4? Yes. 5? Yes. 6? Yes. Right? We can also combine conditions, right? Or I should say logical operators. So we can check, is it greater than 3 or equal to 1? So we basically get the same thing as before, but 1 is equal to 1, so this becomes true. Okay? So we can do all sorts of things with this. It can be really, really convenient. It's kind of difficult to appreciate this without actually trying to implement certain things in code, but I promise you it's really, really worth understanding how to do this. And actually, we're going to see an interesting example in the indexing section. So let's get straight to that. Okay. So indexing an array works basically the exact same way as indexing a list in Python. So here's an example. We're just initializing this array called data, and we can use square brackets with an index to get, for example, the 1th element. Okay, this is exactly how you do things in Python. Note that I wrote print there, just because if I do data at 1, it shows it in kind of this weird format. It's saying it's a NumPy integer instead of just printing out the number 2. But in theory, this is the exact same thing. Okay. You can also take slices, so hopefully you're familiar with that format. This means take all the elements from index 0 to index 2, excluding index 2. So basically everything up to index 1 is included. Okay, so hopefully you've seen that before. It's very useful. And here's a new interesting thing that you probably haven't seen, which is called conditional indexing, or at least I think it's called that. Maybe I made up that name, but it's a nice thing to call it. So basically, what we can do is come up with an array of trues and falses, for example, and if we pass that in as the index, so literally what we're doing here, I'm just going to copy and paste this so you can see, instead of putting in a number like 1 or slicing like 1 to 2, we can paste in a list of booleans, and it's only going to return the elements where the boolean is true, right? So basically it's asking, should I include the number 1? No. Should I include the number 2? Yes. Should I include 3? No. 4? Yes. 5 and 6? No. Okay? This might seem kind of random. When would this come in handy? It turns out that this is extremely useful. So let's see an example. Let's say we have the matrix A, and we want to filter it to get only the elements where A is smaller than 3. And we can define, I call this variable mask, and then we feed that in as input, and it extracts all the elements where A is smaller than 3. But typically, you don't really define an explicit variable to do this. Instead, you just write it like this in this much more concise and I'd say readable format as well. So give me the elements of A where A is smaller than 3. Gives you the exact same result. And as usual, of course, all the same techniques work on higher dimensional arrays. So we have this array of numbers from 0 to 3, and we want only the elements that are greater than 1. Okay? We could also do something like where they're even. So where b modulo 2, meaning when you divide by 2, the remainder is 0. So this gives you only the even numbers in the array. So all sorts of cool stuff you can do there. And it'll come in handy, especially I think in data science approaches. It's great for filtering stuff out. Okay, on to another exercise. Oops, there's a solution again. So this time we're going to try to multiply together the arrays x and y to get a new array, which we'll call z. And then we're going to filter out z to keep only the even entries. Well, I kind of just showed you how to do that. We'll just show the solution right away. So z is equal to x times y. That's the first step. And then to filter out for only even, we take x modulo 2 equal to 0, and we get the even numbers, right? So we only kept the 8 and the 24. Okay, on to probably the most important, but also the most complicated and confusing part of this tutorial. Please don't click off now. This is going to save you a lot of pain if you can understand this, and it's really, really, really useful, okay? Let's get into it. Okay, so like I said, broadcasting is probably the most important thing to learn in NumPy. So let's start off by motivating it with a simple example. So let's say we have a list of numbers. So the numbers from 1 to 3, 1, 2, 3. And we want to multiply each element by 2. Well, the kind of naive way, if you didn't know about broadcasting, would be to remember, hey, we just saw earlier we can multiply two arrays element-wise, right? We can multiply the first element by the second, second by the second, first by the first, second by the second, third by the third, right? So how about we initialize this array called twos, which contains a bunch of twos, and we multiply a by twos. That works, right? There's a problem. This technique does not scale well at all, right? What if instead of the numbers from 1 to 3, I had the numbers from 1 to 1,000? Am I going to initialize an array by typing 2 1,000 times? No, right? Turns out broadcasting is a technique that's going to make this way easier. And it's super, super powerful. I can't emphasize that enough. So how do we do it with broadcasting? So we're going to basically just take a variable b. We're going to set it to the number 2. And we multiply it by the array, and voila, we got 246, exactly what we expected. But that's kind of weird. How are we able to just take a and multiply it by a scalar? So we can do the same thing. We can multiply it by 3. We expect 3, 6, 9, right? What's happening? Why can I multiply it by a scalar when I thought we could only combine arrays? Turns out that under the hood, what NumPy is doing is this thing called broadcasting, where it's going to take the single element array and it's going to stretch it to have the same size as a does, and then multiply those together. So it's kind of pretending that 2 was actually copied a bunch of times and multiplying that with a. Okay, so hopefully this diagram makes that clear. The key idea is this stretching to make two things have the same shape and then combining them afterwards. And it turns out there are actually a couple of rules that work to do this. But before understanding those rules, let's just go through another example. So let's say we have this matrix here, A, which has shape 4 by 3. Okay, so we have 4 rows and 3 columns. We want to add B to every single row. So we want to add 1, 2, 3 to this. We want to add 1, 2, 3 to that, etc., etc. So it turns out broadcasting will let us do that too. Notice that they don't have the same shape, but it's okay. NumPy is going to handle that for us. Basically what it's going to do is it's going to copy B a bunch of times to turn it into a matrix instead, and then add 2 matrices together. Okay? So indeed, if we just do A plus B behind the scenes, NumPy is automatically going to broadcast. There's no need to say, hey NumPy, broadcast this for me. If it sees that the shapes aren't the same, it's going to try to broadcast them and then add those 2 together. It's kind of going to figure out what you want it to do. Not exactly, like it's deterministic. It's not going to be random and guessing. It's more up to you, but you can kind of think of it that way. So we get exactly what we wanted. 1, 2, 3, 11, 12, 13, 21, 22, 23, etc., etc. So what happened? Again, we broadcasted. We stretched it out, right? So here's A from our example. And what we did with B is we copied it down 4 times to get this kind of imaginary matrix that doesn't really exist. And then we add that to A. So we add this first row to that first row, this first row to that first row, etc., etc. And we get the result we desired. So let's get a little bit more precise about this so you can actually predict what's going to happen. So when can you actually broadcast, and when is it going to give you what you expect it to give you? So before broadcasting, NumPy goes through this process of checking whether the dimensions of the 2 arrays are compatible, right? Intuitively, you can look at this and think, yeah, I could copy this because it has the same width as the matrix, right? So if I just copy it vertically, I can get something of the same shape. So basically, NumPy has kind of an algorithm to check, are these 2 compatible? Can I stretch them in certain ways so that they end up having the same shape and I can add them together? Okay, so that's what NumPy is doing. So how does it do it? So it compares the dimensions 1 by 1, so pairwise, and it checks, are they compatible? If it finds one that isn't, then it throws an error and says, sorry, I can't broadcast. Okay, so what are the steps? So first, it takes the shapes of both of the arrays. So here we're working through this example, what NumPy is doing behind the scenes. It takes them and it aligns them to the right. So it aligns the rightmost dimensions. We're not aligning this 3 with the 4, we're aligning the 3 with the 3. Then anywhere where there's a missing dimension, so if A has more dimensions than B, it's going to fill B in with a 1. Okay, so we just go from this to this. So we fill in a 1 right there. Then finally, it's going to check for each pair of dimensions. So we can look at this like vertical lines. We check each vertical pair like this, check if they're compatible. What are the rules to check if they're compatible? It has to satisfy one of the two conditions that I list below. So either one, they're equal. So that's the case with these threes. They're equal. So no need to stretch along that dimension. They're already the same size along that dimension. Or one of them is a 1. So that's what's happening here, right? 1 is a 1, obviously, and 4 isn't. So we're going to copy B 4 times along this first dimension. And then we're going to get a 4 by 3 matrix, and we're good to go, right? So that dimension that we're copying along, right? Basically, this dimension here is the 1, and this is the 3. So we only have 1 here, so we're going to copy it 4 times to make it equal, right? But they're the same along this dimension, so no need for any copying. That's basically it. So we just check the compatibility along those dimensions, and then we copy and stretch it out. And that's it. With that, let's take a look at something that's not compatible. So again, oops, this is the wrong A. Let me just run my code up here. I'm going to run all of this, initialize B as well. So now it should be fine. We get A. So let's take the same A as earlier. And this time try to add a 4D vector. So you might be saying to yourself, well, that seems fine, right? We can add this to each of the columns instead. We can rotate it, but no. Broadcasting will not rotate things for you, okay? So we're going to get an error. We're going to get an error. So what's the problem? We try to add them. We get this error. Operands could not be broadcast together. So what went wrong? Well, remember the rules. We line up the dimensions on the right, the rightmost dimensions. But in this case, instead of 3, we have a 4 here, but 3 isn't equal to 4. So they're not compatible dimensions, and we throw an error. Okay, so you have to keep in mind basically kind of how your vector is rotated. Okay, so we have a mismatch along this horizontal dimension. It's not going to rotate it vertically for us and treat it as a column vector. Okay. With that, let's look at some more interesting examples. So here we have 2 arrays. One of them is 1 by 3. I kind of showed the answer. Hopefully you didn't see that. One is a 1 by 3 vector, and the other one is a 3 by 1. I'm saying vector, I should say array. I'm going to use those interchangeably, but hopefully don't get too confused. So I want to ask you, what is the result going to be if I add these 2 together? So we have a 1 by 3 added to a 3 by 1. Well, turns out we're going to get a matrix. Even though we're adding 2 vectors, we actually get a matrix. Why? Because we're going to stretch A along this first dimension 3 times so that these 2 numbers are the same. And we're going to stretch B along the second dimension 3 times so that these 2 numbers are the same. And we get a 3 by 3 matrix. We can see this in this nice diagram here, right? So this is our first vector. This is our second. We're going to copy this one vertically and this one horizontally, and we're going to get this same guy right here. Okay, so we can kind of summarize this a little bit using these rules. So if we have A, which has this shape, and B, which has this shape, let's see how we end up with this shape here through broadcasting. So first we're looking at the pair 1 and 4. We get 4 because we compared 1 to 4. Those are compatible because one of them is a 1, and we just copy this one 4 times. Here, A and B, 2 and 2, these are the same number. No work needs to be done. They're the same along that dimension. And finally, 3 and 1, those are different, but luckily we have a 1 in B, so we can just stretch B 3 times along that dimension. Okay? So that's it. That's broadcasting. It seems cool. Maybe the first example was the best motivation for it, right? Just like scaling everything in a vector by a certain number, but also adding a vector to a bunch of rows of a matrix is also actually a really common thing that comes up, so it's good to know how to do that. I have this real world example. I'm going to skip it, but basically the idea is you can modify images by adding vectors to all of their channels. But again, we're going to skip over that. But basically we have this image. Image is RGB, and if we add a vector to each of the RGB vectors, we can change its color. Okay, so that's cool. Okay, now before we wrap up this broadcasting section, it's pretty important to distinguish between a array with shape n versus n by 1. It turns out that they behave in different ways, and we actually saw an example of this earlier. You might not have noticed it, but this 1 can make a huge difference. So if we initialize an array with shape 3, right? So let's print a dot shape. It's 3. And then we can also initialize a 3 by 1 array. So there are a few ways to do this. One, we can initialize it in the same way as above, right? So that's what we did in this cell up here. And then reshape it to have shape 3 by 1. That's probably the most intuitive way to do it, but it's not the most common. The second one is to expand the dimensions. So basically we initialize our array like before, and then we expand the first dimension. So we add basically, or along the first axis. So we add this new dimension on the first axis, or this is actually the most common way, but probably the least legible. Basically you initialize your array, and then you index into it, and you say, basically this means keep all the first dimensions that already existed, and then add one where I said none. Okay, so keep 3 in the first position, then add 1 here where I said none. Okay, you're going to see this probably a lot in people's code, so it's good to know. Even though, again, it's not that legible, but once you get used to it, it's actually kind of faster to read. Although probably the most explicit and easy one to read is reshape. Okay, so let's see what happens now if we initialize an array of shape 3 by 4 and we add a. So a was the one with shape 3, not 3 by 1. So what happens? We're trying to add a to each column of C. So maybe what I should do actually is first show you what C looks like, and again show you what A looks like, and then we're going to try C plus A. So what we're hoping for is that we could take this 3D vector and add it to each column. But remember what I told you earlier, NumPy doesn't rotate vectors for you, right? So if we try this, it's not going to work. Basically, the 3 is going to be misaligned with the 4. Oops, we got an error for a different reason. But the problem here is that it tried to line up the 4 with this 3, and they're not equal, and neither of them is a 1, so NumPy didn't know what to do. So here I have a little explanation, right? We try to line these up. We insert the 1s in the missing dimension, and we find that 3 is not equal to 4, so we can't broadcast. So what do we do instead? Well, if we use a 3 by 1 array, this actually works. So remember our goal was to add our vector to each column, which is exactly what we have here, and it works. Okay, so this is what it looks like when we line it up this time. Pairing 4 with 1, that's fine, and pairing 3 with 3, that's fine, so it's compatible, and it does exactly what we were hoping for. Okay, one last example, I believe, of broadcasting. So consider the following 2 arrays. So we have A, which just looks like this. It's a vector. Its shape is just 3, right? And we're going to look at B. So B is a 3 by 3 matrix containing the numbers from 1 to 9. Oh, I didn't run this cell. Geez. Okay. That's what we were expecting. Okay. So our goal is going to be to create a 2 by 3 by 3 matrix, which I've represented as 2 separate matrices, but remember, we can think of these as a stack. And really, I shouldn't say matrix here. I should say array. Okay? But the idea is we want to add these together to get this 2 by 3 by 3 array. Now, what is going on here? Basically, what we've done is this first matrix contains 10 added to each element of this red matrix here. So 11, 12, 13, 14, 15, all the way up to 19. And the second one contains 20 added to 1, 2, 3, 4, 5, 6, 7, all the way up to 9. Right? So how do we do this? Basically, the idea here is we're not going to think too much exactly about how things are being broadcasted, but we're just going to try to get the right shapes. Okay? So let's look at our shapes. So A's shape is 2, and B's shape is 3 by 3. And we want a shape of 2 by 3 by 3. If we think about our broadcasting rules, what we're going to want to do is insert some 1s into A and insert a 1 in this position in B. And then think of when we add these together, 2 aligned with 1 means we're going to stretch B along the first dimension, 1 aligned with 3 means we're going to stretch A along the second dimension, and then we're going to also stretch it along this third dimension because we have a 1 with a 3. And so we run this cell, and we get exactly what we wanted. But why did that work? Let's look at this diagram. So we took A and we reshaped it to this shape, and B and reshaped it to that shape. And then, as I was saying, we check the pairs. Okay, we're going to stretch B twice along this dimension. We're going to stretch A twice along this dimension, three times along this dimension and three times along this one. And we get our desired shape. And it turns out that the desired shape also has our desired numbers inside of it. Okay, so oftentimes, instead of kind of getting lost and thinking about how the stretching is going to work, just try to insert axes in positions such that when you add them together, you get the right shape. And more often than not, it's also going to give you the right result. Okay, so it's kind of a leap of faith. You should definitely verify your result, and eventually you'll be able to be quite confident in the result. But this is a nice thing to start with when you're not really used to thinking in terms of broadcasting. Okay, so really the key takeaway here was that we inserted axes along certain dimensions so that when we add them together, we get this result. Okay, and basically this dimension here is just the maximum of each pair of numbers, right? The maximum of 2 and 1 is 2, maximum of 1 and 3 is 3, maximum of 1 and 3 is 3. Okay, but I showed you guys this syntax earlier, and it's probably what you're going to see a lot of the time. We're using this none keyword to insert axes in certain positions, but we get the exact same output. Okay, on to the next exercise. So we're going to start off kind of easy. Add x to each row of y. Okay, so what is it? Well, x is pretty easy to visualize. Hopefully y is as well. It's a matrix of zeros. So we want to add, we want 1, 2, and 1, 2. How do we do that? Not really much work needed. We literally just do x plus y, and we get what we want. Now, instead of adding to each row, we want to add to each column, okay? And as a hint, remember that I told you guys there's a big difference between a vector with dimension n versus n by 1, right? You're going to have to use that in this exercise. Okay, so you can try it out here if you want. But the solution is to insert an extra dimension right here so that x has the following shape. And then when we do x plus y, the dimensions line up, right? 2 paired with a 2, 1 paired with a 2, we get a 2 by 2. But this time we add column-wise instead of row-wise. Okay, exercise 3. We're going to insert axes to each of the following arrays such that the result is a 2 by 3 by 2 array. Okay, so let's look at our shapes here. X dot shape, Y dot shape. So where should we insert axes so that when we add these, we get a 2 by 3 by 2? Give it a shot. I'll show you the solution in a moment. Okay, so the solution is we insert axes. Maybe I'll show you what's going on here. So basically we're turning x into a 1 by 3 by 1. We're turning y into a 2 by 1 by 2. So let's just do this. Print its shape. We'll do this. Print its shape as well. And you'll see that what's the maximum of 1 and 2? It's 2. 3 and 1 is 3. And 1 and 2 is 2. Okay, so that's broadcasting. It's a lot to wrap your head around. It'll come with practice. Please make sure you understand these exercises. Send me questions on Slack if you have anything that doesn't make sense here, or talk to me during the lectures. Okay, finally, we're almost done. I know this is getting long. I don't know how long this recording is. Maybe we're getting close to an hour. These two are going to go by a lot faster, so don't worry. Hang in there. So we're going to look at axes and built-in NumPy functions. So we saw earlier that our arrays have axes. I didn't really mention them just because I didn't want to overwhelm you. But we basically have the 0th axis, 1, 2, whatever, 3, 4, 5. Depends on how many dimensions you have, right? But basically, it's important to understand where the dimensions, where the axes are in your array because you can apply certain built-in NumPy operations along a given axis. So let's look at an example. Let's initialize this 3 by 3 array. And if we want to take the sum, so add together, all the numbers along axis 1, so along the rows, we use a.sum, and then we specify the axis, right? So 3 is the sum of 0, 1, and 2. 12 is the sum of 3, 4, and 5. And 21 is the sum of 6, 7, and 8, right? But if we wanted to add along the columns instead, no surprise here, specify the axis to be 0 instead, right? So sum 0, 3, 6 gives you 9. And finally, if you don't specify an axis to one of these built-in functions, it'll instead just add up everything inside of your array. Okay, so this is really useful. Maybe you have a matrix and you want to add up all the numbers along the rows because the rows represent, I don't know, a certain sample in your data set or something. You can just add along the rows. Okay, and there are a lot of other functions that behave in the exact same way but just do different things. As in, you can specify an axis or not specify an axis, and you'll either get everything along that axis or globally if you don't specify an axis. But it's things like the mean, so you take the average along a row, the standard deviation, the maximum, the minimum, etc. Right, so here's a little example. If you do specify an axis, then you use maximum, then you'll get the maximum numbers along that axis. If you don't, then it's just going to give you the global maximum, minimum, or sum. Okay, so that's it. These are really useful though. They're going to come up a lot in your code, especially taking the mean and the sum, but also sometimes things like maximum and minimum. Okay, finally, let's just put it all together with kind of a practical example that would probably come up in your assignments, and that's taking the mean square error. If you're watching this right now, it's possible you haven't seen the mean square error before, but I think you have because it's in lecture 1. What's the idea? You add up the difference between your predicted y value and the actual y value. You square that, and you take the average. Okay, so what does this look like? Basically, we fit a line to our data, and we're checking the squared distance between our points and the line. So these purple dots are our y, they're actually our yi's, and our y prediction is this line. And we're just adding up how far we are from the line in each case. So how do we do this in NumPy? It's actually really easy. So if we have an array containing all our predictions and another one containing all our labels, so label is like our actual data points, and predictions are the points along our line, then we can take the difference between them, right? So that's this part of the formula. We can square them using Python squaring, which is turned into NumPy squaring, and then take the mean. And that's it. That's how you compute the mean squared error in a single line. Okay, so that's it for the video. We went over a lot. Hopefully it wasn't overwhelming. But this is going to carry over to all sorts of other things, like working on PyTorch, for example. So hopefully this all made sense. In previous years, we had a much briefer tutorial, and I think people struggled. So hopefully this will help you out on your assignments.